This is a walkthrough of Problem 2 on Exam 2 in Module 3, which is on page 70 of the book Problem Solving Guide for Electromagnetism and Optics. Problem 2 is the equipotential lines in a field region are parallel and 5 centimeters apart, as shown in the figure. Conventionally, the voltage falls in the direction of the field. Therefore, the direction of the electric field in the figure is to the right. That's where the voltage is going down. It's dropping. 25, 0, minus 25. Field is to the right. What's the magnitude of the electric field at point A? Part B, a particle with a mass of 50 micrograms, net charge of plus 50 nanocoulombs is shot in from the right. It's going, what's the speed right here? Comes in here, goes up the hill, and stops at the 0 line, and then comes back down the hill. What was the speed of the particle? We know the mass, we know the charge, and we know that it experienced a change in voltage of 75 volts. So let's think about part A. What is the magnitude of the electric field at point A? You can't get anything from knowing the potential. This 0 volts, you can't get anything from this. You can't get any information about the field because you have to get a change. It's like asking, I'm on the surface of some planet and I have a mass that's up in the air and it's got a potential energy of 1,000 joules. What's the gravitational field? You have no idea what the field is. You can't get the field from that information. What you need to do is drop the thing and see how quickly its energy changes. We know here that it changes by 25 joules per coulomb in 5 centimeters. The rate of change of the voltage with distance is the field. We have a good diagram. The voltage drops 25 volts in a distance of 5 centimeters. So the field is 25 volts per 5 centimeters. That's the same as 5 volts in 1 centimeter and 500 volts in a meter, which is also 500 newtons per coulomb. That's part A. Part B. We have a charge right here. It goes up a potential hill of 75 volts, and then it goes back down the hill. We can get the change in kinetic energy. It's Q delta V. Charge is 50 nanocoulombs. Change in potential is 75 volts. Look at the units here. This is a kinetic energy, and it had units of coulombs volts. Coulombs volts. What the heck is a coulomb volt? Well, if you express voltage in the natural unit of joules per coulomb, then you understand what's going on. I have this many coulombs, and the change in kinetic energy is 75 joules per coulomb. So I'm going to get joules. That's the kinetic energy. And I get 3.75 times 10 to the minus 6 joules. It ends up at rest. It stops here after 75 volts. So it must have started with 3.75 times 10 to the minus 6 joules of kinetic energy. We know the kinetic energy. We know the mass. 1 FmV squared. It's 50 micrograms. It's not 50 microkilograms. A microgram is 10 to the minus 6 grams, but we have to go all the way to kilograms. So we need 9 orders of magnitude. 50 times 10 to the minus 9th kilograms is 50 micrograms. So I just solve for V. One equation, one unknown. The initial speed of the particle, 12.2 meters per second, right here. That's problem 2.